white and black stripes. These have often been called zebra stripes.
Geologists know that the Earth is like a giant magnet with a north and a south pole. But the magnetic poles aren't fixed. Every 300,000 years or so, the magnetic field suddenly flips 180 degrees. When the field flips, a compass that was previously pointing north will swing to the south.
This reversing of the Earth's magnetic field is a very interesting and exciting but very puzzling phenomenon for geophysicists to explain.
Scientists think this reversal explains the stripes either side of the ocean ridge. In the 1960s, geologists discovered that molten volcanic rock, known as magma, swelled up from deep underground to create the ridges in the Atlantic and Pacific. As magma wells up between the tectonic plates, it pushes the seafloor up and forms the colossal mid-ocean ridge thousands of feet high. When the rock is hot and molten, its magnetic minerals line up with the north-south direction of the Earth's magnetic field. As the magma cools, the minerals are locked in position. These rocks act as a permanent record of the magnetic pole's location when the rocks were formed. As more and more magma is forced up, the old crust is pushed away from the ridge and records the reversals in the Earth's magnetic polarity.
If you have reversals of magnetic polarity, then the seafloor acts sort of like a tape recorder and records these changes in magnetization. Then the pattern of magnetic stripes allows people to calculate the speed at which the plates are moving apart.
The zebra stripes are proof that over time, the seafloor in both the Atlantic and the Pacific is spreading away from the ridges at a rate of more than 2 inches a year. But geologists needed proof that magma created the ridge. If red-hot molten rock is forming the enormous mountain range in the Pacific, the surrounding water should be warm. In 1977, a team of scientists set out to discover whether this warm water really existed. Dudley Foster was the pilot for these historic dives.
It's been an exciting occupation because you're on the cutting edge of science. New discoveries all the time. Every cruise, there's a new group of scientists with new scientific objectives, and there's the exploration and the discovery. And that's really what puts the thrill in the job.
For weeks, the crew scanned the undersea mountains without success. And then they hit the jackpot. A bizarre pillar of rock, spewing hot, toxic gas.
And we saw the water was sort of shimmering, sort of like bubbling in a glass teapot or something. We stuck the temperature probe in there and measured 38, 39 degrees Fahrenheit, which was really amazing because the ocean's a huge heat sink. So to see something warm like that was kind of startling.
In these pillars of rock, the expedition had found the heat from the magma surging up from deep inside the Earth. It wasn't warming the water evenly along the ridge. It was channeled up through strange hydrothermal vents.
When you make these discoveries, you don't know how significant they are. The true significance of them maybe takes several years to appreciate. And this was one of those times.
For the investigation into the Marianas Trench, these vents are a decisive piece of evidence. They confirm that magma is continually creating new crust at the Pacific Ocean ridge. And magnetic zebra stripes prove that old crust is pushed away from the ridge towards the other side of the Pacific Plate, towards the Marianas Trench. But this presents scientists with a puzzle. If new crust is being created at the ocean ridge and the Earth isn't expanding, then the old crust must be disappearing somewhere else.
The reason that there's not getting bigger with seafloor spreading is because the same amount of seafloor is being destroyed in the Pacific.
Something in the Pacific Ocean is devouring the seafloor, and all the evidence points to the Marianas Trench. In the hunt to discover what formed the Marianas Trench, scientists now know crust created at the ocean ridge is being devoured somewhere and by something in the Pacific Ocean. They suspect the Marianas Trench is involved. But the proof would come not from the trench, but from these. The Mariana Islands, a chain of volcanoes that break through the ocean surface 200 miles west of the trench. Scientists noticed the island chain mirrors the trench's exact shape. This led them to think the trench was responsible for the island's creation.
If you see pictures of the Marianas Trench, it's curved, and the line of volcanoes that it generates is curved exactly parallel to it.
Geologists believe that the trench formed the volcanoes. Subduction. Subduction occurs where two tectonic plates collide. As they grind past each other, the heavier plate is pushed beneath the lighter plate. The descending plate is forced down into the Earth's intensely hot interior called the mantle. It takes with it water and sediment built up over millions of years.
Volcanoes form above subduction zones not because the Earth is hotter there, but because this is where we're taking the water that once was in the ocean. It's taken into the mantle and gets sweated out, causes the mantle to melt, and this magma is what then rises and erupts explosively out these volcanoes.
The water in the sediment forces magma to swirl up and push through the plate above. And when it breaks the surface, it creates volcanoes, like the volcanoes that form the Mariana Islands. It was subduction that formed the islands west of the trench and gave investigators the breakthrough they'd been looking for. Because here, at last, was a process powerful enough to create the Marianas Trench. As the descending plate dives down, it digs into the mantle. Here, the colliding plates form a trench, a giant crease in the ocean floor. It seemed that scientists had finally explained how the trench was formed. There was just one problem. A very large problem. Around the world, subduction zones cause violent earthquakes and catastrophic tsunamis.
We know subduction is happening because of the active earthquakes, and these are the most devastating earthquakes. This is the earthquake that generated the tsunami in Sumatra. Also, the other very large earthquakes in Alaska and Chile.
But the Marianas Trench, the deepest subduction zone in the world, hasn't caused a devastating earthquake since records began in the 17th century. Investigators needed to know why.
That's the $60,000 question.
They hoped the trench's shallower western edge might provide the answer. Here they found an intriguing chain of underwater hills 2 miles below the surface of the sea. Engineers drilled down into the hills and collected core samples. And when the scientists analyzed the samples, they discovered the hills were actually volcanoes. And they spewed out not lava, but mud. The fine, powdery mud is made up of a soft type of rock that has been ground up in the subduction zone. It seemed this soft rock might explain why there have been no major earthquakes at the Marianas Trench.
Everybody has a sense of what a volcano is, but not all volcanoes erupt igneous rocks. There's some volcanoes that erupt mud, and a certain kind of, an unusual kind of mud in the Marianas is made out of serpentine. And serpentine is a very weak rock, and it can be scratched with a knife or something like that.
Investigators realized the grinding plates crush the soft rock to form a lubricating mud that prevents large earthquakes. Then the mud bubbles up to the ocean floor, where it forms the strange mud volcanoes found along the trench's western edge.
Other parts of the world, like the Andes or maybe Indonesia, you've got two plates that are grinding together, and one of the plates is quite strong. And it takes a big earthquake to rupture that plate interface. But if these rocks are weak, like they are in the Marianas, where you've got these serpentinites, those are very weak, and it doesn't take much energy at all to get the two plates to glide one past the other.
At last, geologists had discovered what created the Marianas Trench. 50 million years ago, the Pacific Plate slipped under the edge of the Philippine Plate. As it bent and dived into the Earth's mantle, it formed the colossal Marianas Trench. And the plate is still moving. Like a giant conveyor belt, the Earth's crust travels slowly across the Pacific Plate, from its birthplace in the East Pacific Ridge to its graveyard 10,000 miles away in the Marianas Trench. Today, the Pacific Plate's movement can be tracked in real time.
Confirmation has come from GPS technology, where we can actually put a transmitter on an island and come back year after year and actually follow it moving a few centimeters a year towards the trench.
It's devouring the crust at a rate of 3 inches a year, about as fast as a human fingernail grows. Every 4 million years, it swallows an area the size of the United States. By consuming the crust created at the Pacific Ocean Ridge, the ravenous Marianas Trench is the world's largest recycling plant. But there was one remaining and major piece of the puzzle to find. Scientists still didn't know why it is the deepest trench on Earth. They suspected the age of the seafloor at the bottom of the trench may provide the answer.
It turns out there's a really strong relationship between the age of the seafloor and its depth in the water.
In 1999, a team of deep sea drillers returned to the trench to collect core samples.
One great thing about drilling the ocean crust is we actually got pieces of it. So we're holding in our hands here the material that's actually getting subducted at the Marianas Trench, and it turned out to be 170 million years old. So we can say with confidence that's the oldest ocean floor before it's getting swallowed up in the mantle at the trench.
But why is this piece of rock the oldest on the ocean floor?
The seafloor at the Marianas Trench is so old because it's been so long since it was born. So it was born in the equivalent of the Eastern Pacific today, and it's just been going on longer than any other place in the oceans before it's been subducted.
The Pacific Plate is the planet's largest tectonic plate, covering an area 11 times the size of the United States. When crust bubbled up at the ridge 170 million years ago, it was light and buoyant. But as it traveled 10,000 miles across the plate, it cooled and became compact and dense. Over millions of years, the dense crust got heavier and began to sink into the mantle below. Scientists realized that because the crust at the Marianas Trench is the oldest ocean crust, it's also the heaviest and so has sunk deeper into the mantle than any other area of ocean crust. Here at last was the explanation for the trench's extraordinary depth. The picture of the Marianas Trench is almost complete. Volcanic islands mirroring the trench's exact shape lead scientists to believe it runs along a subduction zone. And slippery mud volcanoes explain why it doesn't create large earthquakes. But one question remains unanswered. Towards the trench's southern end, the vast chasm drops a further 2 miles to its lowest point, the Challenger Deep, 7 miles beneath the waves. The question is, what makes it plunge so deep? The investigation into the Marianas Trench has one final puzzle to solve. At the trench's southern end, the sea floor plummets a further 10,000 feet into a 7-mile deep chasm called the Challenger Deep. It's the lowest point on the planet. But so far, scientists have been unable to explain why this one section of the trench is so deep. Now, they believe the shape of the descending tectonic plate may hold the answer.
The Challenger Deep, in addition, is a little bit deeper because of some peculiarities relating to how the slab that's going down is behaving.
A narrow slab of crust has torn away from the Pacific Plate's descending edge.
Well, it's basically got to do with how the slab pushes the mantle out of the way. Where you have a narrow slab, like you have at the Challenger Deep, it can sink almost vertically because the mantle that it's trying to displace can move around out of the way.
Investigators have finally unraveled the mysteries of the Marianas Trench. And in the process, they've made a discovery with implications that stretch far beyond the trench itself. Studying the ocean ridges led geologists to believe that magma welling up at the ridges was pushing the plates apart. But the exploration of the Marianas Trench has changed this idea forever.
People used to think that maybe the magma would kind of push the plates apart. And that idea is largely discounted now.
As the ocean crust travels from the Pacific Ocean ridge to the trench, it changes from a buoyant, red-hot magma into a colder, denser, and heavier crust. The plate's leading edge becomes so heavy that it drags the rest of the plate along behind it.
The heavy, cold plates at the trenches are sinking down into the mantle and pulling the plates apart at the ridges, and the magma just passively fills in the gaps.
The investigation into the Marianas Trench has revolutionized our understanding of how the Earth's plates move. We now know a worldwide network of subduction zones drag tectonic plates around the globe, powering the movement of continents over millions of years, and moving the very Earth we stand on.
The plates that are moving fastest on the Earth are the ones that have all the trenches.
The Pacific Plate is the fastest moving of the 9 major plates on the planet because it is surrounded by dozens of destructive trenches like the Marianas. They are consuming the ocean crust faster than the ocean ridge can produce it. Over millions of years, the Pacific Plate will shrink until sometime in the distant future, the largest ocean on Earth will disappear. Australia will crash into the United States, reshaping our planet. Perhaps one day, downtown Seattle will compete for real estate with a suburb of Sydney, Australia. And all because of subduction zones like the Marianas Trench. But for all its significance, man has only ever dived to the bottom of the trench once, and there are no immediate plans to return.
Imagine asking someone, what is the flora and fauna of California? And saying that someone spent 10 minutes there, picked up 2 ants, come back, and said they've sampled California. That's probably how well we know the Marianas Trench.
To date, less than 5% of the world's oceans have been explored. But only by returning to the ocean's very deepest reaches will we fully comprehend the incredible forces that recycle and rebuild our world.
The way I like to think of it is that ocean exploration leads to new research questions. And if we don't have exploration, we don't even know the right questions to ask.
It is now known what a geological wonder the Marianas Trench is. Since this deep chasm in the Earth's crust was first discovered with a length of rope and a lump of lead more than a century ago, evidence has piled up. A record-breaking dive to the lowest point on Earth. Giant undersea mountain ranges with bizarre magnetic zebra stripes. Proof that the ocean crust is spreading towards the hungry Marianas Trench, lined with slippery mud volcanoes which prevent devastating earthquakes. And the planet's oldest ocean crust, the reason that the Marianas Trench is the deepest point in the oceans. In the darkest and most remote place in the world, scientists have added to their knowledge about the powerful forces that contribute to the dynamic story of our planet.